Okay, good day. This is Coshocton Mathematics Department, Pre-Calculus, Blizzard Bag 2 for January 25th, 2022. I am Mr. McCulley. Let's get right to it to keep this short. Hopefully yesterday's wasn't too bad. Today we're going to be doing some exponential review. We're going to solve some equations where the variable is an exponent, and we're going to solve application problems involving exponential equations. So a quick review of a couple of things that you've seen before, and just two properties of exponents and logarithms that are going to be important to us today. If you take the logarithm of an exponential, you can actually take that exponent and bring it down front, and that's what's going to allow us to solve for variables that are in the exponent. And then an additional one, if you take the ln of e to some exponent, it is just that exponent. And if you look back in your notes, we went over proofs for both of these. But to keep it short, I'm not going to do that in this lesson today. I'm just going to assume that they're true. A couple of exponential specific use functions. The general exponential function is always f of x is equal to ab to the x. And we use this for some compound interest, simple interest, and continuous growth functions. The simple interest function is a equal to p times 1 plus r to the t. The compound interest, a equals p times 1 plus r over n to the nt. That is our compound interest formula. And our continuous growth formula is called the PERT function. A equals PE raised to the RT. In each case, the principal or the initial amount is the P. The rate as a decimal for a percentage. So if they give it to, say, 5%, when you plug it into any of these equations, it's going to be 0.05. N equals the number of compounds. For example, if it says compounded daily, then N is going to be equal to 365, and T is the time unit. In most instances, the time unit is going to be years. So with that, let's get into a couple examples. We're going to solve the following exponential equations. And so here we have this equation. So we're going to follow the rules of exponents. And I am going to do all of the work here before I go to the calculator. And I'm going to make one calculation in the last step. You do not have to do that. If you want to make a calculation where you have a value on one side of the equations and you just want to keep reducing it, that is perfectly okay as well. So here's what we're going to do here in this first instance. First thing we're going to do here is we are going to divide by 5. And so I'll have 34 over 5 equals 3 to the x plus 2. And so now I got to get this exponent down. So I'm going to use that first rule that we talked about. I'm going to take the ln of both sides so that I can use this property and bring that exponent down. So here, ln both sides. So I'll have the ln of 34 over 5 equals the ln of 3 to the x plus 2. And so here I'm going to use the property log base a of x to the n is equal to n times log base a of x. And I'll bring that down. Now I have to bring it down as a quantity. So we'll have the ln of 34 over 5 equals x plus 2 times the ln of 3. Now I can calculate the ln of 3. That is also a number. So here I'm going to say divide by ln 3, and then in this step we're also going to flip it. I'll flip the equation. So I'll have x plus 2 left on that side, and then I'll have the ln of 34 over 5 all over the ln of 3, and here we will subtract 2 from both sides. Alright, so we're going to subtract 2. We'll go x is equal to the ln of 34 over 5 all over the ln of 3, and then subtract 2. Now we can just take that, go to Desmos, and we're going to need a few parentheses here, but we'll start by doing the denominator. It was the ln of 34 divided by 5, and then we'll close those, and then we'll divide by the ln of 3 and then we will subtract 2, and we'll get this 2.551. Now we can check that if we want. We can plug that back into our original equation, and we can say 5 times 3 raised to, and I'll need parentheses, and then we'll just cut and paste this. So we'll copy that, and then we'll come down here, and we'll go paste, and then we'll go plus 2, and we get 34. So we feel very confident in that answer. All right, next one. Mr. McCulley invests $5,000 in a retirement account, fixed annual interest rate compounded continuously. After 10 years, the balance reaches $9,500. What is the interest rate of the account? So right off the bat, we're just, since it says compounded continuously, we think A equals PE to the RT. I'm just going to go through and make a list of all my values. So 5,000 is what I'm investing. That's my initial amount. P equals to 5,000. And an annual interest rate, we're trying to figure out what the interest rate is. So R is my unknown. My time is 10 years. And my final balance, A, is 9,500. All right, so I can just plug in, and we'll have 9,500 equals 5,000 e to the r times 10. All right, so we're solving for r, and since r is an exponent, we're going to need that property of exponents where we take the logarithm of both sides. So first thing we're going to do is we're going to divide by 5,000. And so I'll have 9,500 over 5,000 is equal e to the 10r. And so you'll notice I've got this big number here, and it's thousands. I can technically cancel out the zeros, and I could actually reduce it more, but at this point it's half dozen on one, 6 to the other. That's just an easy reduction. And so I'll say take the ln of both sides. So I'll have the ln of 95 over 50 equals the ln of e to the 10r, and I'll say remember that the ln of e to the x is just equal to x. So I can rewrite this thing as the ln of 95 over 50 equals just 10r. Here we're going to divide by 10, and so we'll also flip it here. I'll have r equals the ln of 95 over 50 all over 10. That I'll plug into my calculator, so we'll go right to decimals. And we'll say the ln of 95 divided by 50. We'll close that parenthesis, divided by 10, and we get 0.0641. And we will write that there, 0.061485. And so we'll round that, and we'll say R is equal to 6.149%, because we had to round. That is our answer. All right, the final example for today. Georgianne invests a sum of money in a retirement account with a fixed annual rate of 3% compounded monthly. After 15 years, the balance reaches $4,500. What is the initial amount of the investment? All right, so let's, again, it says compounded monthly, so we're talking A equals P times 1 plus R over N to the NT. And let's see here. So she invests the sum of money. P is my unknown with an annual fixed rate of 3%. So again, our R is 3%, which will change to 0.03. After 15 years, the time is 15. The balance reaches, so my final amount is equal to $4,500. So we want to know what was the amount of the initial investment. So I have all of the variables except for the one that I'm looking for. I can plug in. I'll go 4,500 is equal to P times 1 plus 0.03 all over, N, apologize, didn't know N, but compounded monthly. There are 12 months in a year, so we'll put a 12 down there, and then we'll go 12 times 15 up here because I have 15 years, and P is the only variable that I don't have. This expression here is calculable, even though it looks kind of ugly. So I can say that P is going to equal 4,500 divided by this whole thing. So we'll just go 1 plus 0.03 over 12, all to the 12 times 15. Now you can calculate this if you want, just go 45 divided by whatever that is. But I'm going to plug it into my calculator as is. So we're going to type in 4,500 divided by parenthesis 1 plus 0.03 divided by 12. We will close that parenthesis, and then we will raise that, and we need parentheses to do the multiplication. 12 times 15. And so our initial amount is this 2,870.94 cents. It's dollars. 2,870.94. All right, that's all I have for today, folks. So the Macaulay fun fact of the day: Macaulay loves bad movies from the 80s, and you should watch them. Buckaroo Banzai, Big Trouble in Little China, and Flash Gordon are all gloriously bad movies that you should watch during your snow day. Have a great day, folks. Goodbye.